Problem set 6 has 4 problems associated with it, and we're going to explore more of this issue of absolute entropy and a little bit some of the thermodynamics of the Gibbs energy function. So in the first problem, we're given that there is a particular equation called the Sackur-Tetrode equation, a very famous equation, in which we can relate the entropy of a system that has only translational motion to the various molecular parameters. Okay, so it's actually a very interesting equation. It's giving us an absolute quantity of entropy in terms of such things as the mass of the particles, the volume, the number of particles in the system, and then of course things like Planck's constant and Boltzmann constant that are also part of this equation. So in effect, what this is telling us is that based on these very fundamental features, if you will, of a molecule, one can actually derive a quantity, the absolute entropy, just based on those principles. So this is a really great illustration of how microscopic properties can be converted into macroscopic quantities like entropy. All right, so we're going to use this expression to compute the entropy for 1 mole of a neon gas at 360 Kelvin. So essentially the number of atoms is going to equal Avogadro's number, and the mass of neon is this in grams per mole, or Daltons, so you'll need to convert that into appropriate units so that things convert. Now, I will tell you, this is a reasonably straightforward substitution problem where you just need to calculate something, but I'll tell you that in practice you need to really keep track of your units. And the reason I say this is it's very easy to make mistakes in doing this because there are so many quantities involved. So be sure you're using the quantities in the units that will cancel out properly. The argument of this log function should have no units. So in other words, you need to choose units for each of these quantities that will cancel each other out. All right, out here the Boltzmann constant, well, if we have n is equal to Na, then Na times Kb is simply the gas constant. All right, so that will give you a little bit of an easy way to get to some results here. But you'll ultimately need to report your answer in joules per, I believe, joules per mole K here at for this particular part of the problem. All right, you are given a molar volume, by the way, which you can use in place of this V over N. All right, now the second part is simply a exercise in how does this value that you get depend upon the mass of the particles. So if everything else was the same about this system, 1 mole of particles, but instead of neon we had a gas that was of mass 44 instead of 20 Daltons. The question is, how much would the entropy content change? So what you'll need to do is to calculate the entropy for the mass of 44 and subtract the entropy that you calculated up here for a mass of 20 and report that difference. All right, it's a measurable difference, so I think it's an interesting exercise to undertake. In the second problem, we're going to be now going a step further. We've done this for translational motion and generated the Sackur-Tetrode equation, which, by the way, is based upon this this relationship between entropy and the the system partition function. But now we're going to do this for vibration and rotation. Now, the point here is that 44 grams per mole is the same as the atomic mass for carbon dioxide. But carbon dioxide also has vibrational and rotational contributions. So how do those play in? How big are those contributions relative to the one we've just computed for the entropy of translation? Well, we're going to use this version of the equation for absolute entropy, but we're going to restrict our consideration just to the rotational motion in part A. So I want you to think about how this thing gets modified, if you will, or specialized so that it's only treating rotational motion. So we're going to pretend that the translations aren't happening and no vibration is occurring, only rotation is occurring, and that's going to contribute a component to the overall entropy of the system. We're then going to do the exact same sort of exercise, but for vibrations in the second part of this problem. So in this case, we're going to be using the partition function for vibration to carry out a similar sort of exercise where we're going to get the absolute entropy that is due to the vibrational motions in carbon dioxide. In this case, we have 4 different vibrations, and they have these particular frequencies. You'll notice that 2 of them are degenerate, and that has something to do with the geometry of carbon dioxide. We're also going to be relating these vibrational energies relative to their lowest state, just as we did in one of the problems in the previous problem set. So we're going to treat the state where V equals 0, so it has energy of 1/2 h bar omega above the minimum of the potential, but we're going to treat that as the 0 of energy. So 0 of energy is here, so all of the other energies are basically related relative to that energy. That results in a partition function that looks something like this. All right, so these are reasonably, I think, good exercises for exercising this particular formula for the absolute entropy, and helps you to illustrate how the vibrations and the rotations contribute to this in a molecule. All right, in problem 3, we're going to now consider just an isobaric process. So just one sort of things. Isobaric, remember, means that the pressure doesn't change. There is no change in pressure, and it's going to expand in volume between these 2 quantities. And the whole idea is that when it expands, it's going to change its temperature from 320 to 560 K. Now, so obviously what's driving the expansion here, because pressure is constant, is we're heating it up. And by heating it up, we cause the gas to expand. So we've given a heat capacity for the system and an initial entropy, and I'll talk in just a minute about where that might be important. And we'll need to calculate the following changes. We need to calculate the delta H and the delta S. And both of these, I think, can be done relatively straightforward for the isobaric process. All right, there are, I think, good formulas, and hopefully you are familiar enough with these now to know what that means. I will note that when pressure is constant, this is the heat capacity that you care about, not constant volume heat capacity. So isobaric process, how does one calculate enthalpy and entropy? We're then going to go down here to the third part, where we're going to be trying to calculate the change in Gibbs energy. Now, there is a practice problem in lesson 3D that illustrates exactly the process that you need to go through for this. And that's when you're going to need to know the initial entropy content. All right, I'll refer you to that practice problem, which has a recorded solution, so that you can get a handle on this. But I guess another hint is that you're going to need to use the general expression, the general definition for Gibbs energy in order to solve this part of the problem. All right, finally, in problem 4, again, we have a multi-step process, and this is drawn out on a PV diagram for you. In this case, however, we're not doing a cyclic change. We're just doing a change from one point on the PV diagram to another point. So the whole idea is we are going from here to here. But we're doing this via 2 different pathways. One pathway is a change at constant volume that goes from the top point down to this point, and then followed by a horizontal change that goes from the midpoint to the final point. And the other is simply an isothermal expansion that goes from our initial point to our final point. And that's the curved path here. So you either have 1 and 2 added together, or you have 3, but both processes end up taking you from the initial point up here to the final point down here. All right, so what do we need to do here? Well, in the first case, we're going to simply find the volumes V1 and V2. We're given the pressures for P1 and P2, pressure here and the pressure down here, and we're given the temperature of the initial point. We need to calculate the 2 volumes. I'll leave it at that. I think you should know how to do this by now. And once we do that, you'll need to then report the change in volume that occurs for this process. All right, once you've done that, then for each of these three paths, you will need to calculate these thermodynamic quantities: the internal energy change, the enthalpy change, and the entropy change. Now, I will note that one of the pieces that you're going to need for all of this is the temperature at this intermediate point when you're doing the path 1 plus path 2. You'll need to find what T0 is in order to do this calculation. All right, but otherwise I think it's reasonably straightforward, and certainly you've seen plenty of examples for how to do this sort of process. All right, now Gibbs energy is a state function, and so it's going to be the same for both pathways. This is the thing about these state functions. For a cyclic process, they are 0 for the cyclic process because your initial and final point is the same. But if you're going between two discrete points, it doesn't matter what path you follow, a state function will have the same change. So delta U, delta H, delta G, delta S, all of these are state functions, and so all of them will have the same net value independent of the path that you take. So what I want you to do is now evaluate delta G for the net process and report it in kilojoules. And you can do this any way you like. You can use path 3, you can use path 1 and 2. You should get the same answer regardless.